Good day, everyone. Today we will be discussing about rejection region. So last week we discussed about basic concepts of testing hypotheses. So this is just the continuation of our topic last meeting. So we learned about identifying the parameter, the null and alternative hypothesis, and at the same time we also learned how to find the confidence level, level of significance, and identify what type of test are we going to use in a given problem. Today we will be discussing or illustrating how are we going to know if we're going to reject or accept the given null hypothesis. Let's try discussing the given example. But before that, let me discuss to you about what is a rejection region. Critical region, also known as the rejection region, describes the entire area of values that indicates you to reject the null hypothesis. In other words, the critical region is the area encompassed by the values not included in the acceptance region. It is the area of the tails of the distribution. So this definition is from CLMD Statistics and Probability module of Region 4A, Calabarzon. Now, here is the illustration of rejection region. So as you can see, this is what they call one-tailed. This two, one-tailed. The type of test is one-tailed, while this one is what they call two-tailed. So when are we going to use this type of normal curve wherein there is a critical value here and the shaded part is here? So we're going to use this, or we're going to draw this type of normal curve if our alternative hypothesis has a symbol or has a sign of less than. So if it is less than, it implies that we're going to have this kind of normal curve. However, if our alternative hypothesis has a sign of greater than, it implies that we're going to have critical value here and then we're going to have shaded part at the right side. Now for two-tailed, so if we have two-tailed, that's the reason why if we're going to write the critical value for two-tailed, that's positive and negative. Because we have positive critical value here and negative critical value here. Now we're going to have this one and then we're going to shade on the left and the right side of the normal curve. Now, the question is, how are we going to know if we're going to accept or reject the null hypothesis? Just take note of this one. This unshaded part is what we call the acceptance region, while this shaded part is what we call the rejection region. If we're going to plot our test value or computed value and it falls on the unshaded part, it implies that we're going to accept the null hypothesis. However, if we're going to have computed value or test value and it falls on the rejection region or on the shaded part, it implies that we're going to reject the null hypothesis. Let's try an example. A banana company claims that the mean weight of their banana is 150 grams with a population standard deviation of 18 grams. Data generated from a sample of 49 bananas, randomly selected, and the computed value is 1.45. Is there sufficient evidence to reject the company's claim? Use alpha 0.05. So let's start with the hypothesis. For null hypothesis, we're going to first, before we identify the null and alternative hypothesis, we're going to identify the parameter. The parameter is based on what is being claimed on the given problem. So it is claimed that the mean weight of their banana is 150 grams. So it implies that mean is mu is equal and then 150. So that's the reason why our parameter is mu equals 150. So now, in order for us to identify the null hypothesis, just always remember, once you said null hypothesis, there exists no difference between a parameter and a specific value. That's the reason why, once you have null hypothesis, we're going to use always an equal sign. And then for alternative hypothesis, we have three symbols or sign. It's either greater than, less than, or not equal. Because once you set alternative hypothesis, there exists a difference between a parameter and a specific value. So, however, in this problem, since our parameter is equal, automatic we're going to have not equal. When are we going to use greater than and less than? If that is written on the given problem. Now, n is the number of sample size. So, as we can see, the number of sample is 49 bananas. So, we're going to have 49. Now, the confidence level, we already know this. However, the confidence level is not given on the given problem. However, alpha is 0.05. So, therefore, we already know that that is the level of significance. So, to find the confidence level, we're going to convert the level of significance into percent. So, 0.05 will become 5%. Subtracting this by 100, it will become 95%. Now, for a property test statistics, we're going to use t-value. Why? Because we already know that n is equal to 49, which is greater than or equal to 30. And we already know that the population standard deviation is, or sorry, this is z, rather. Going to erase. This is z because n is greater than or equal to 30. Again, we will only be using p-value if n is less than 30. And at the same time, we use z because the population standard deviation is known. How are we going to know if the population SD is known or unknown? It is known if the given standard deviation is population. But if the given standard deviation is just a sample, automatic population SD is unknown. Again, I'm going to repeat. It will be known if the given on the given problem is population SD. However, if the given on the given problem is sample SD, it implies that your population SD is unknown. But since on our given problem, the given is population standard deviation, automatic it is known. For the type of test, since we have not equal for this one, our alternative hypothesis is not equal, automatic, our type of test is two-tailed. Again, when are we going to use two-tailed or one-tailed? It will be two-tailed if the alternative hypothesis is not equal. But if the alternative hypothesis is greater than or less than, automatic, we're going to use one-tailed. Now, for computed value, it is given. Computed value is 1.45. Now, for critical value, you're going to take a look on the t-distribution table. On the bottom part, you're going to see the z. Now, since we have z, you're going to take a look if it is one-tailed or two-tailed. Since it is two-tailed, you're going to take a look on two-tailed, 0.05. So, now, as you can see, z, two-tailed, 0.05. You can see that the critical value is 1.96. However, since this is not equal, our critical value is positive, negative 1.96. Now, if we're going to plot this one, 1.96 will fall here, and negative 1.96 will fall here. So we're going to have this one. Then, after that, we already have the shaded part, or we already illustrate the rejection region. Now, we're going to test if we're going to accept or reject the null hypothesis. Now, to know if we're going to accept or reject the null hypothesis, let's plot the computed value. As you can see, we can plot 1.45 here. 1.45. So, as you can see, the computed value falls on the unshaded part. Since it falls on the unshaded part, it implies that we're going to accept the null hypothesis. Okay, let's try another example. A survey reports the mean age at death in the Philippines who suffered from COVID-19 is less than 65 years old. An agency examines 25 randomly selected deaths and obtains a mean of 68 years with sample standard deviation of 8.51 years. At 1% level of significance, with computed value of negative 2.85, test whether the null hypothesis of the problem will be accepted or rejected. So the first thing that you're going to do, identify the parameter. Let's identify the parameter. For this problem, we can see that mean age at death in the Philippines who suffered COVID-19 is less than 65 years old. So automatic, we have mu less than 65. So now let's identify the hypothesis. For null hypothesis, we already know that that is always equal. So we have mu equals 65. Now for alternative hypothesis, we will just simply copy our parameter, which is mu less than 65. Now for n, we're going to identify the number of sample, which is 25. Now for confidence level is not given on the given problem. However, the level of significance is given, and that's 1%. So automatic, that is 0.01. For confidence level, we're going to subtract 100 and 1%, and it will be equal to 99%. For appropriate test statistics, since our n is less than 30, automatic, we're going to use t-value. At the same time, the given is sample standard deviation and not population. That's the reason why population SD is unknown. Now, for type of test, since we have less than, automatic, we're going to use one-tailed. For computed value, it is written computed value of negative 2.85. Now, in order for us to find the critical value, you're going to take a look on p-value. And then, the first thing that you're going to do, identify first the df. Since our n is equal to 25, our df is 24. So, take a look on df 24, one-tailed, and 0.01. So, you're going to take a look on df 24, one-tailed, and level of significance, which is 0.01. As you can see, the critical value is 2.492. Now, we're going to decide about the sign. Are we going to use positive, negative, or positive, negative? But since our given is less than, automatic, our critical value is negative. It will only be positive if the alternative hypothesis has a sign of greater than. And it will be positive, negative, the same with the first example, if the given alternative hypothesis is positive or not equal. So let's now plot negative 2.492. And then let's now shade this part. And then after that, we're going to decide if the given null hypothesis is accepted or rejected. Now, taking a look on our computed value is negative 2.85. So as you can see, this is negative 2.492. So if we're going to plot the computed value will fall here, negative 2.85. So as you can see, the computed value falls on the shaded part. Since it falls on the shaded part, we already know that that is rejection region. So therefore, we're going to reject the null hypothesis. Okay, let's try another example. For our third example, the mean time consumer waits in line before checking in a grocery chain is greater than 10 minutes. To verify the performance of the store, the obtaining mean time of 15 customers is 10.5 minutes with sample standard deviation of 1.6 minutes. By calculation, the computed value is 1.21. Use this data to test the null hypothesis that the mean time is 10 minutes at 0.01 level of significance. So let's start with identifying the parameter. Our parameter is mean time is greater than 10 minutes. So we're going to have mu greater than 10. So now, in order for us to identify the hypothesis, just always remember for null hypothesis, we have mu equals 10. For alternative hypothesis, we have mu greater than 10. We will just simply copy the parameter. For n, we're taking a look on the number of samples. As we can see, we are dealing with 15 customers. So we have 15. For level of significance, we have 0.01. And in order for us to find the confidence level, we will just simply subtract 100 by 1%, and that is 99%. Now, in order for us to find the appropriate test statistics, since our n is less than 30, automatic we're going to use t. And at the same time, we're dealing with sample standard deviation. Since we're dealing with sample standard deviation, automatic the population SD is unknown. Now, for type of test, since we're dealing with greater than on our alternative hypothesis, automatic our type of test is one-tailed. Now, how about the computed value? Computed value is on the given problem, which is 1.21. Now, in order for us to find the critical value, since we're dealing with p-value, we're going to start looking for df. Since our n is 15, our df is 14. Now, how are you going to get the value of degree of freedom? Again, df is equal to n minus 1. So, therefore, we're going to take a look on df 14, one-tailed, and 0.01. So, taking a look on your t-distribution table, df 14, one-tailed, 0.01, we're going to get the value which is 2.624. Now, how about the sign of the critical value? Since our alternative hypothesis is greater than, automatic the sign is positive. Now, let's plot the critical value and draw a rejection region in our normal curve. So, 2.624 will lie here, or lies here. Now, the question is, are we going to accept or reject the null hypothesis? So, let's now plot the computed value. The computed value is 1.21, and if we're going to plot that, 1.21 will fall here. So, as you can see, the test value or computed value falls on the unshaded part. So, thus, it implies that we're going to accept the null hypothesis. So that's all. Thank you and God bless everyone. So please don't forget to subscribe on our channel, hit the notification bell button so that you're going to be updated with our video tutorials. Thank you and God bless again.